Now to something magic. I promise you one of the magics of nature. Here it comes. Central limit theorem. Maybe the reason why the normal distribution is called the normal distribution. And funny enough, it's about normal distribution, but actually you could say that the topic of this little part is actually about non-normal data. Remember what I told you up here, the theory that took us to the formula for the confidence interval. We'll do a bit more detail on that later, but in that theory, I assumed that the population distribution, this little f thing that describes the population, was a normal distribution in the first place. So I assumed that the natural phenomenon that we are sampling from behaved like a normal. Many natural phenomena does behave like the normal, so fine. But far from all phenomenon that we are studying will behave like normals. We talked about the log normal, we talked about the uniform. Yeah, we even talked about discrete distributions, which by definition, of course, would not be normal. None of them. But here's the great news. Here's the fantastic, brilliant, amazing, breathtaking, emotional, tear-breaking news to you. No matter what, and that's a big statement, right? No matter what. Couldn't be bigger, actually. The distribution of the mean, the sampling distribution of the mean, will be approximately normal. It doesn't matter. The x could be uniform. It could be log normal. It could be binomial. It could be Poisson. It could be exponential. It could be any one of those 150,000 distributions that you didn't get a name for in this course. No matter what, when I look at repeated means, and if I just have the money enough to go high enough on the n, if n is large enough, it's approximately normal. So the error I make in saying something about the mean, no matter what the initial behavior is, behaves like, at least approximately, like a standard normal. So we can at least use the normal distribution to say something about the error no matter what hits us. That's a pretty big thing. Can you get the picture? Whoa. If n is large enough, we can do statistics for the mean based on the standard normal distribution. Whoa. That's one of the big ones. Now you just opened up your toolbox from one little phenomenon of normal behavior to all types of behaviors. If I just have n large enough, I can use the normal to be intelligent about the mean of all sorts of behaviors. I mean, yeah, I'm having difficulty even finding I could start jumping also. I feel like both crying and laughing at the same time right now. It's fantastic. So I'll do neither. CLT in action. Let's look at the uniform distribution. Hopefully this is just to illustrate it for you. And maybe take a bit of the magic out of it, because it's not really magic. It's just fantastic. I am simulating here, in some odd way, I'm simulating in the first go, 1,000 times I'm simulating one uniform number using R uniform. And then in a funny way, I'm taking the average of the one number 1,000 times. The average of one number, that's the number itself, right? But now I did the code to extend it a little bit in a sec. And then I show you how the uniform distribution looks like. This is a picture you could have seen last week when you were introduced to the uniform distribution on the interval 0 to 1. The uniform distribution is the random distribution that has the same probability of having an event anywhere in the interval between 0 and 1. It's uniform. There is the same probability to be between 0 and 1/10 as we have being between 0.9 and 1. It's the uniform distribution, the even distribution. The density is flat. Here's how it looks when you simulate. Here is how it looks if I simulate 1,000 means of 2 uniforms. Right? Just a little extra thing. I mean, the R technique is not the important thing, but just as an explanation, I take 2,000 uniforms and I put them in 2 columns, right? So 1,000 times I have 2 uniforms next to each other, and then I compute the mean 1,000 times. That's actually this little neat apply function in R. If I put in like this, apply on the matrix, dimension equal 1 and the mean, it computes 1,000 means and put it in another matrix or vector depending on the dimension. And then I make the histogram of those 1,000 means of 2. Uniform means of 2 uniforms. It's almost normal already. What's happening? It's the CLT in action, central limit theorem in action. Well, it's not particularly magic, right? Because when I simulate 2 uniforms, they will tend to be, of course, not each, both of them will not be exactly the same place. It's completely random where they are. Then when I take the average of 2 things, right? Here are 2 things, I take the average, it goes towards the center. So averaging takes things towards the center. So it's more likely to have, the average of something will more likely be in the center than being in the extremes. That's almost obvious if you think about it like that, I hope. So when I average 2, it's more likely to have an average close to the center. It's no longer a uniform, right? The average of 2 uniforms does not behave like a uniform because it's more likely to be close to the center than to be close to the extremes, because to be close to the extremes, I would have to have 2 extremes after each other. And that's a bit more unlikely to have 2 of sort of more spread out after each other. And then if I do 6 or 30, here is how the means, 1,000 means of 30 uniforms look like. That's almost exactly a normal distribution, right? So means of other distributions behave like normals if n is large enough. The practical consequence is that the CI method that I gave you, we will allow ourselves to say that even though theoretically it was deduced based on a normal assumption that led us to the t distribution actually. If you're a bit into the math about these distributions, yeah, you can either take a class on probability if you want, that's highly recommendable, or you can start out by looking at some of my extra math videos, podcasts, where you can see not very formal proofs, but some at least proof sketches of mathematical kind. If you're into that, it can be proved that the t distribution follows as a consequence of the normal and all that, but it's not a syllabus of this course. For here we just use it as a probability fact. But of course we have a problem still. We have a problem because in practice, how should we decide about whether n is large enough to just ignore the original distribution and just use the normal or the t? Well, that's a very difficult and impossible question to answer in general. We will have some simulation tools later on in the course that will help us more on this issue. But for now, the rule of thumb is if n is larger than 30, that's an easy rule, right? Don't take this rule into court in your later life, and then don't try to sue me for $1 billion or something because this rule took you into problem. So it's not a rule that will be valid in a in a courtroom, but for in this course it's a rule of thumb, and for many distributions it's okay enough. And even for some distributions, as we saw with the uniform, for smaller n it could even still be okay. Symmetric distributions are pretty rapidly turning into normals, whereas grossly asymmetric distributions would need really high n. And yeah. That's The central limit theorem. Wasn't that amazing? We can use the confidence interval. We can make standard errors on a mean for any situation. And here's the big news. Anything that is computed in science, all scientific papers, hundreds of thousands of results given to people, to the world, used in business, all of those are means or functions of means. So now we can make a confidence interval for all distributions. As Arthur Benjamin was his name, in his TED Talk says, something plus minus 2 standard errors is a generic rule that can be used almost everywhere. At least if it is adapted in the intelligent way, it can be used everywhere. The front page of our book, that's the CLT picture. Well, look at those questions and try to find, I'm sorry about that. I'll just leave this is an error on my side. Something went wrong. Bugger. I'll just let it go now, and then we'll see. At least we still have the no on the top. Sorry about that. I'm a bit worried about the last 2 ones because I wonder if something went wrong down the line of saving this one. But let's see what happens.